welcome to 5.4, where we are going to start to bring it all together as far as integration is concerned. We're starting to wrap things up with this course. So in this section, I really want to kind of bring it all together, talk about the main focus of integration, definite integrals, indefinite integrals, which is what we're covering specifically here, antiderivatives, relating that stuff to the applications of area, which is the main application that we hit. And then in 5.5, that last section will just be a new technique to integrate more things. So really this is going to be the spot where we start to wrap it all up and say, it's coming to a close. It's time to say this is what we got. So as far as Calc 1 goes, once you've got this Chapter 5 under wraps, remember that when you move on to Calc 2, and I'm assuming you are moving on to Calc 2, if this is your last calculus or math course in college, then congratulations. This is the last hurdle you got to jump. But if you're going on to Calc 2, say you want to be an engineer, or you want to be a physicist or a doctor, and maybe you need some Calc 2, or maybe even Calc 3, just remember that in Calc 2, Chapter 5 from Calc 1 is probably going to be the most helpful chapter. Differentiating is not a hard task once you get the hang of it and know the rules. Integration is always going to be some sort of artistic technique that you have to constantly be on your toes with. It takes practice. It just takes practice. So, again, wrapping it up in the big picture here, this section is going to be pretty important, and so will the next section. It'll be very important when you go on to Calc 2. So, right off the bat, indefinite integrals are different than definite integrals. When we looked at definite integrals, we had lower limits and upper limits of integration. We knew what we were plugging in. And when we looked at the fundamental theorem of calculus, we knew where to plug those in. But for indefinite integrals, when we look at a function and we want to integrate it, but we don't have any bounds to consider, then we should be finding the general antiderivative f of x and leaving that plus c, because we're not evaluating this at the upper limit and then at the lower limit and getting a positive c and a minus c when we do the subtraction, thanks to the fundamental theorem of calculus, part 2. Here we're not doing that, so we do need to take into account that what this is a general antiderivative, and an antiderivative of a function could have a constant, and we don't know what that constant is because we don't have enough information to say, oh, this was the original function and this is the derivative. We don't get to go that direction. We're working backwards, and because we're working backwards from a function lowercase f to get a general antiderivative, when we're walking backwards, we don't get to see what was there in the first place. So since we don't get to see what was there, we put that plus c as a constant because it could have been there. So what this means is that if I were to differentiate f prime of x, I should get f of x. Right? That's what this means. If I anti-differentiate lowercase f, I should get capital F of x plus c. And if I differentiate this capital F of x, I should get lowercase f of x. I'm leaving out the plus c here because c is just a constant. We all know if we differentiate it, we get 0. So even if I were to write it here and say, hey, differentiate this entire left-hand side, then I would have to include a big set of parentheses that says differentiate all this stuff, give me that prime. You'll still get lowercase f of f because that plus c is not going to matter once you hit the derivative. So to clean up the notation just a little bit, that's why I'm saying, hey, if you differentiate this piece, you should get back to f of x. That plus c really isn't going to matter once you differentiate it. It's going to be gone forever. But if you want to see it, then I would write it like this. Since we're differentiating and finding the derivative of the left-hand side, we're taking the derivative of capital X, and we're also taking the derivative term by term of this constant. It's gone. We just get f prime with the capital F prime to be lowercase f. So again, it's a back and forth. If I integrate lowercase f, I get capital F with the antiderivative. If I differentiate the antiderivative, I get back to the lowercase f, the derivative. So it's a simple back and forth, but there are no bounds to consider. You simply integrate and you stop. Right? And that's the nice thing. You integrate and then you're done. Right? As long as you tack on that plus c, then you're good to go. So since we know about derivatives, and we know some popular derivatives, like if we differentiate the function f of x equals sine of x, we get f prime of x equals cosine of x, right? The derivative of sine is cosine. So we know that. And then we just work those backwards, right? If we know we're starting with cosine and we want to integrate that or anti-differentiate that, we should be taking cosine, integrating it, and getting back to sine, because the derivative of sine is cosine, so the antiderivative of cosine is back to sine. So there are also some popular antiderivatives. These are the ones that we see most often. Let me take one of these. Should be new, probably that squeaky one. Yeah. So here are some popular integrals that we come across very, very often, especially towards the end of Calc 1 and especially in the beginning of Calc 2. So here are some popular integrals, and these are indefinite integrals. They're not going to have an upper and a lower bound. I'm not going to number them because there's quite a bit of them. And you'll probably catch the vibe pretty quickly about what's happening here. We're just taking a general antiderivative. If I have the integration of a constant c, then I get back my power of x, and I get a plus c. Maybe so that you don't think these are the same, maybe I'll use a capital C for the constant. They're not necessarily the same c. This is a lowercase constant. This will be a capital C, or maybe I can even call it C1, so you know that it's not exactly the same. That could be a different c. So, for example, if I'm integrating 5 with respect to x, notice 5 is just a constant function. There's no variable x. But I do need to pick up this function 5x plus c, because if I differentiate 5x plus some constant, I should get the number 5 as its derivative, which means the antiderivative of that 5 should be a function of this form 5x plus c. Again, since I'm only going one direction, I don't have the information to pick up that c, so I just want to leave it. The general form is going to be plus c. If you tell me that the antiderivative of 5 is 5x plus 1, I'm going to say, why not 5x plus 2? Why not 5x plus 3? Why not 5x plus a billion? Why not 5x plus negative 50? Why not 5x plus pi? You had no idea what that constant was, so you're not allowed to claim what that constant is unless the problem provides more information, or if you have a definite integral that gives you the upper and lower limits of integration. Here we don't have that, so we're just stuck with the plus c. If we're integrating x to some power, and we take that power and look for an antiderivative, we're going to have to add 1 to that power, but we're also going to have to divide by that new power. Again, whatever this number is, n plus 1, I'm going to have to divide by it. Why? Because if I differentiate this entire right-hand side, n plus 1, which is a number, comes down as a multiple and cancels out with the denominator, and I subtract 1 from n plus 1, leaving just n. It's exactly the function I was integrating. So by differentiating the right-hand side, I get the left-hand side. By integrating the left-hand side, I should get the right-hand side, right? And that is a constant marriage between these two: derivative, antiderivative, derivative, antiderivative. You should always be able to bounce back and forth and not have any discrepancies. So that's what we're looking for. So this is like the power rule, but it's the power rule for anti-differentiation, not the power rule for differentiation. So for example, if we have the integral of x to the 5th with respect to x, this is an indefinite integral. I don't have bounds to plug in, but I still can integrate it, but I need to divide by that new power 6. Again, I challenge you, differentiate this. The 6 comes down, cancels out with the denominator 6, leaving just x to the 5th when I reduce the power by 1. If I do not have that division by 6 there, you are going to get 6x to the fifth when you differentiate. This is not 6x to the fifth. You have the wrong integral. All right, so these two need to agree. When you differentiate the right, you should get this left-hand integrand. When you anti-differentiate the left-hand integrand, you should get this function on the right-hand side. More popular ones. We've actually seen this in the last section. And there's a reason we put the absolute value bar there, because we don't know really where x is in terms of on the real number line. So to cover our butts, we really want to put an absolute value bar there. There are no limits of integration, so who's to say x might be negative? Well, then this would not make sense. So we put the absolute value bars there so that it does make sense. We would say we can really only actually figure out that this integral exists and is meaningful to us in the real numbers as long as it's taking a positive log, or a log of a positive value, I should say. If you start taking logs of negative numbers, you start getting into this weird complex stuff, and to most of you that probably sounds a little gross. To me, that sounds like yay fun. The integral of e to the x is e to the x plus c, because again, if I differentiate this right-hand side, I will always get e to the x back. The reason that plus c is there, because I'm differentiating it to get back to e to the x, so the constant disappears. But when I find the antiderivative, or the indefinite integral, I should be able to replace that plus c, because it could have been there. Now, c may have been 0, but I can't claim that because I don't know. I don't have enough information. If we integrate sine of x with respect to x, we get negative cosine of x plus c. Why is the negative there? Well, because if you differentiate cosine, you get negative sine. That's not negative sine. But if I differentiate negative cosine, I get negative sine. Aha, the negatives cancel out. That's how I properly get this derivative to spit out positive sine. For cosine of x, well, if I differentiate sine of x plus a constant, the constant disappears, I differentiate sine, I get cosine. So I don't have to worry about that negative sign anymore. So that one looks pretty nice. Secant squared of x is the derivative of tangent of x. Therefore, the antiderivative of secant squared of x must be tangent of x. If I differentiate tangent, I get secant squared. If I integrate secant squared, I'm back to tangent, etc., etc. You can see what's happening here. From right to left, right to left, right to left, right to left, right to left. Those are all derivatives. Now we're undoing that left to right, antiderivative, left to right, antiderivative, left to right, antiderivative. And you'll notice as you anti-differentiate, or aka find an indefinite integral, this plus c is always popping up. So I'm not going to give you an extensive list, but just enough so that you can start to see the pattern. And by now you probably see the pattern here. When I differentiate cotangent, I get negative cosecant squared. If I differentiate negative cotangent of x, I get negative cosecant squared of x. And that's why I'm getting this positive integral of cosecant squared of x to be negative cotangent of x plus c. So again, these are just some popular ones that we see often towards the end of Calc 1 and then the beginning of Calc 2 that we should be familiar with. Try to think of a function such that when you differentiate it, you get secant of x times tangent of x. There you go. It's secant of x. But don't forget your plus c. So if you differentiate secant of x plus any constant, the constant disappears and the derivative of secant is secant tangent. So right to left is differentiating, left to right, there's your antiderivative, aka your indefinite integral. Some more popular ones. Cosecant of x, cotangent of x. When you integrate that with respect to x, you get negative cosecant of x plus c. more popular ones. This one you'll see quite a bit. Everyone tends to love this. 1 over x squared plus 1. When I differentiate a function, I actually get 1 over x squared plus 1. So when I anti-differentiate 1 over x squared plus 1, I get that popular function back. Guess what that function is? Yeah, it's arctangent, or aka tangent inverse of x. But I need the plus c to be tacked on. Here's another popular one that deals with an inverse trig function. It's 1 over radical 1 minus x squared in the denominator, and that is arcsine of x. Because when I differentiate arcsine of x plus any constant, well, the derivative of arcsine is this guy. So when I anti-differentiate this 1 over square root of 1 minus x squared, I get back to arcsine of x. But I don't know if there was a constant there or not, so I save my skin by writing plus c every time. And then, well, I wish I had just an inch more space or so, but might as well get them down. Again, we don't deal too extensively with the hyperbolic functions, but these just work out so nice. Because remember, the hyperbolic trig functions like this, you don't have to worry about that sign change. When you differentiate sine hyperbolic of x, you get cosine hyperbolic of x. When you differentiate cosine hyperbolic of x, you get sine hyperbolic of x. So going backwards the other way, the same thing, no sign change. If I anti-differentiate sine hyperbolic of x, I get cosine hyperbolic of x. If I anti-differentiate cosine hyperbolic of x, I get sine hyperbolic of x. So those hyperbolic functions don't have that sign change, S-I-G-N, positive negative sign change, not sine as in the sine function. That is, in my opinion, as a teacher, one of the very worst things about teaching a trig course. If you've had me for trig, you've probably heard me say it over and over again. I have to declare when I mean sine, S-I-N-E, versus sine, S-I-G-N. Gets a little confusing. Oh, the woes of a math teacher, right? All right, so we've got some popular integrals. Obviously, those are not all of them. Obviously, there are a ton more. Obviously, there are a bunch of functions out there that we're not ready to anti-differentiate yet. Again, we need to build these skills. And in Calc 1, we're really just scratching the surface. In Calc 2, you'll get a lot deeper and a lot better at finding integrals, finding indefinite integrals, finding definite integrals, learning techniques of anti-differentiation. So it'll be a lot more involved later on. Let's take a look at some examples, and like I said, in this section, really try and wrap up the big picture of what does Chapter 5 really want us to do? What does Chapter 5 expect of us? How are we going to finish this course and be prepared to move on to the next course? So, when it comes to differentiating, we spend a lot of time learning techniques and ways to differentiate functions. When it comes to anti-differentiation, there's not a lot that we do at the end of Calc 1. There is a lot that they save for Calc 2. So again, we're only scratching the surface. I kind of want to make that clear, and hopefully I've made that very clear here. Let's say we want to evaluate this general indefinite integral of 2x cubed plus secant squared of x with respect to x. And I'm putting these parentheses here because there's addition. The terms are separated by addition or subtraction. If I run the risk of writing it like this without that, then it looks a little sloppy, like I'm anti-differentiating this, and then I'm just adding some weird differential later, right? So to keep everything inside the operation of anti-differentiation, we put those parentheses there because they're separated by plus or a minus. And we did the same thing with limits when we wrote a limit of something that had extra terms in it, 1 plus 2 plus 3 plus 4 plus 5 terms, however many terms there are. We put them all in parentheses to maintain that they're all in the limit. So here's what we want to do. I'm simply going to rewrite it. And I'm going to say that this means term by term. This is the really nice thing about anti-differentiation, or finding an indefinite integral, is I get to do it term by term, much like I get to do when differentiating. I get to do it term by term. Anti-differentiating, I also get to do it term by term. So I could split this up into two integrals and do each piece. Now, quite often we don't write this step because we're very comfortable, once we practice learning how to anti-differentiate, that we know we're going to do it in our head this term and then this term. So sometimes we just do this term in our head and then do this term in our head. And by that I mean anti-differentiate 2x cubed. You will get 2, well, let me write it out, 2x to the 4th divided by 4. Raise the power plus 1, divide by that new power. So again, I'm being very explicit there before I simplify. Plus, then I integrate secant squared. The general antiderivative of secant squared is tangent of x. So the only thing I need to do is make sure I get the most general form by adding on that plus c. So again, I do it term by term. There it is. If you want to split it up and then do it term by term, obviously you get the same result. Now, I never want to leave 2 over 4. That's just sloppy. I'm going to write 1/2 x to the 4th plus tangent of x plus c. So there's my final answer. It is the most general form for the antiderivative of this function. So I've found that indefinite integral. I don't have upper or lower limits to plug in, so the plus c just remains because I don't have enough information to tell you what that constant was. So again, a lot of this is just going back to 4.9, where we started talking about anti-differentiation. This is a lot of that same technique. Let's say we want to find this integral, 3e to the x plus 2x squared, and that's what we call this. We call this an integral. Right? If someone says, hey, you come across any good integrals lately? Oh yeah, cool, try integrating this, right? That's what we're doing, we're integrating. So anti-differentiation, boy, that's a lot of syllables, right? Anti-differentiation. No one wants to say that every time. So we just say the integral, or integrate, right? Rather than saying, hey, can you anti-differentiate this? We say, hey, can you integrate this? It's just easier to say. So you'll probably not hear that word anti-differentiation once you get to chapter 5 and you start talking about integrals. They mean the same thing, essentially. So here is my integration. I'm going to do it term by term. Now, this is just a multiple of 3. So again, we could spend the time writing it out so that we integrate this term plus, then we integrate this term. Since that's a property of integration that we saw in the previous sections, the integral of a plus b dx is the same thing as the integral of a dx plus the integral of b dx, where a and b are functions of x. Well, we could write it out separate. Then we have these multiples, which are just real numbers. So rather than looking at the antiderivative of 3 times the function e to the x, I can look at 3 times the antiderivative of e to the x. Rather than looking at the antiderivative of 2x squared, I can look at 2 times the antiderivative of x squared. Right? Since it's just a nice scalar multiple, we can pull those out front. Again, that's a property of integration that we get to do. So the question is, I'm really integrating this e to the x function, and then I'm just multiplying it by 3. Well, the derivative of e to the x is e to the x, so the antiderivative of e to the x, also e to the x. Now, I don't have to do a plus c here, plus 2 times the antiderivative of x squared is x cubed, but I have to make sure I divide by that new power 3. Now I'll put on the plus c. So when I put on the plus c, I don't need to put a plus c here and a plus c here and say plus 2c, because then I'm doing a constant plus another constant is plus 2 times a constant, which is just plus some other constant. Double a constant is still a constant. So rather than being redundant with a plus c, a plus c, a plus c, a plus c, a plus c for every term, we just save it to the end. Just save it for the end. You know that some of this stuff is going to have constants involved, so just wrap it up in the end and say, hey, guess what? There's some constant involved. Whether it's plus 1 and plus 2, why write that when I can write plus 3? And that plus a constant is representing the constants that are coming from every piece of that antiderivative. So it wraps it up nicely just by leaving it like that. And that's fine. I'm okay with that, but again, you might see 2/3 in the back of the book or something like that. Or you might see 2x cubed up top and then 3 on the bottom. Right? It just kind of depends the way they write the answer, whatever fits nicest. But they all mean the exact same thing. Algebraically, they are equivalent. They all mean the same thing. Let's see if we can evaluate the indefinite integral of 1 plus x over x quantity squared dx. Now, right off the bat, a lot of you are going to say, oh, I'll just do this to the third power and divide by 3. This is not a variable x, right? You're not just going to take this thing and add 1 to the power. That's not how you differentiate. If I gave you a complicated expression like this, you wouldn't just subtract 1 from the power. No, this would be like if I told you to differentiate this, you'd have to go through some quotient rule, some chain rule, right? There's lots of processes. Well, same thing happens for anti-differentiation. You can't ignore the fact that this is a rational function and just make it a cube. That's not the antiderivative, because if you wrote this out all to the third power and tried differentiating that, there is no way you are ever going to get this function back, which means your antiderivative was completely wrong. The way you tried to do it by just adding 1 to the power was completely wrong, didn't work out. Because if you differentiate that and don't get back here, you know you're completely wrong. So what we have to do is play around with this and get it into some functions that we're familiar with anti-differentiating, which means, yeah, algebra, right? No reason to forget your algebra, right? Not at all. There's no excuse. That's like getting your driver's license. You get your first car, and then 10 years later, you decide, hey, now I got some money, I'm going to buy a Porsche. So I don't need to know how to drive anymore. I'm past that. Whoa, you're going to crash, and it's going to hurt. And say goodbye to your brand new Porsche, right? Just because you're in calculus doesn't mean you get to forget your algebra, right? You're based on that foundation. So I am finding the antiderivative of, here's my common denominator, x, laid out. Aha, I know how to anti-differentiate the 1 over x function. X over x is just 1. That's a constant. I can find the antiderivative of that constant. So what you're looking at is 1 over x plus 1 quantity squared dx. But again, don't just give me log x and x. You're ignoring the square. We don't have a technique for chain rule just yet. In fact, in 5.5, when we get to substitution, we'll start figuring out some nice methods to handle nastier functions. But for right now, we can't just say, oh, there's log x and there's 1. Why? Because that would be the antiderivative of this function. This function is not the same as this function being squared. Therefore, it can't have the same antiderivative. So what can we do? Aha, more algebra. Again, there's nothing stopping us from actually distributing that out. Right? We can actually take this, it's being multiplied by itself again. We could square it out. And again, at this point, it should be, nobody should be doing, I'll square that and I'll square that. That's not how squaring things work. We're taking this entire quantity and multiplying it by itself again. That's how you square something. So we square it out. I'll be explicit with some arrows here. 1 over x times 1 over x. Well, that means I get 1 over x squared. 1 over x times 1, well, there's 1 over x. But then my inner term's 1 over x times 1. There's another 1 over x, so I have 2 over x. Last times the last, 1 times 1 is 1. That's some hard stuff there, right? Okay, so what am I actually finding the antiderivative of? X squared is in the denominator, so that is x to the negative 2 power. Again, don't just add 1 to this power and say it's 1 over x cubed. You're not anti-differentiating. You have to add 1 to the power when that power is in the numerator. Negative 2 plus 1 is negative 1. You should be getting x to the negative 1 for your antiderivative. Lots of people will just jump on this and add 1 to the 2 power and say, oh, it's 1 over x cubed because 2 plus 1 is 3. We don't have a rule that lets us handle that power rule for derivatives in the denominator, and we don't have a rule that lets us handle that power rule for antiderivatives in the denominator. So we move it up. Plus, this is 2 over x, which is the same thing as 2 times 1 over x, and I know how to find the antiderivative of 1 over x. I'll just have to double it. Plus 1. We had a property that says when you find the integral of 1 dx, and a lot of times we'll just ignore writing the 1. That just means we're integrating 1, not 0. If it was 0, we would explicitly write 0. So let's go for it. Add 1 to this power and divide by that new power. That's x to the negative 1, which means I have to divide by negative 1. Because again, if I differentiate this, the negative 1 comes down and should cancel with the denominator's negative 1 to give me x to the negative 1 minus 1, which is negative 2. Perfect. Plus, I have 2 times the antiderivative of 1 over x is natural log of x. I put the absolute value bars to save my skin. Plus, integrate 1, you should get back that variable x. Because if you differentiate x, 1x. If you differentiate 1x, you get 1. So the antiderivative of 1 must be x. What am I missing? Technically, when I find each of these antiderivatives, there could be a constant, there could be a constant, there could be a constant. But I didn't write a constant on every one and then add all those constants to then add a constant that's different on the end. I'm just simply going to write plus c to signify to the reader, to the person doing the work, to my boss that I hand my solution to, hey, guess what? There might be a constant. It's indefinite, meaning we don't know exactly what that constant is. So I'm just cueing you in to say, hey, careful, there could be a non-zero constant there. Not enough information for me to tell you exactly what that value is of that constant because it's not a definite integral. So I'm giving you fair warning and saying, hey, here's a plus c. And yes, at this point, I'll say it if I haven't said it already. If you do not put the plus c, you are wrong. Sorry, there's just no way around it. If you do not put plus c, you're wrong. You do not have the general antiderivative. You have one very specific antiderivative, because if you do not put a plus c, you are telling me that the constant must and always has to be 0 for this antiderivative. And you're wrong, because it doesn't have to be. It could be plus 5. It could be plus negative 2. It could be plus pi. It could be plus radical 3. It could be plus a billion. There's an infinite number of possibilities you're leaving out by leaving out that plus c. Yes, it's that important. I'm sorry. It may seem like a really small afterthought, but it is like extremely important. I can't stress it enough that how important that plus c is. So it does have to be there. Okay. Some more examples, because at this point it's just exposure. How do I integrate? Well, you just expose yourself to as many functions as you can and try to integrate them. And by that, I don't mean just writing down a random function. There's a pretty good chance if you just wrote down a random function that you might not be able to integrate it. Because again, there's lots of nasty functions out there that you need a lot more skills in order to be able to integrate. So some of the ones that they give you are designed so that they can be integrated at this point. So let's say we want to evaluate the indefinite integral of secant of t times the quantity secant of t plus tangent of t. Lots of t's flying around. And we're integrating with respect to t. So what that tells us to do is not come up with a general antiderivative in terms of x, because they're telling us our variable is t, so we'll just stick with that variable t. Okay. Well, right off the bat, there's a product of two functions that I have to be careful about. This secant function is actually being multiplied by these two terms, secant of t plus tangent t. So I'm going to distribute so that I get secant squared of t, and I know how to find that antiderivative. That's one of the popular ones. Plus secant of t times tangent of t. That's another one of those really popular derivatives, or sorry, popular antiderivatives that I can find. And again, I can write it out so that I integrate secant squared of t first with respect to t plus, then I integrate secant t tangent t with respect to t second. But in my head, I'm just going to do it in one big shot. Integrate this. The derivative of secant squared of t is tangent of t. And then I'll do this second in my head. The antiderivative of secant of t tangent of t is just secant of t. Don't forget your plus c on the end. Again, if you're thinking, I don't know if I got this correct, differentiate this. Right? Differentiate tangent of t plus secant of t plus any constant. The constant will always disappear when you differentiate it. The derivative of secant of t is secant t tangent t. The derivative of tangent t is secant squared t. So working backwards, I can pick up that function because this function has a derivative exactly like this, meaning that this function has an antiderivative exactly like this. They go back and forth. Anti-differentiate, go from this to this, down. Differentiate, go from this to this, up. Anti-differentiate again, back here. Differentiate, back here. Anti-differentiate, differentiate, anti-differentiate, right? So you're always bouncing back and forth. So you're always picking up, or you're always checking your work in that regard. Again, something a little different. Here, let's say we want to evaluate x over 5 minus 5 over x with respect to x. Again, first identify this is an indefinite integral, so I don't have to plug in any bounds. I just need to find the most general antiderivative. So do be careful about this. It looks weird, but really what's happening is I have 1/5 x. Right? This is just the power x to the first. Right? This is just being divided by 5. So I have 1/5 of x. That's very easy to integrate x. Minus, here is 5 times 1 over x. Again, that's a very specific derivative, so it has a very specific antiderivative, the natural log function. And then again, I just do this one first. So that 1/5 is just a constant multiple. I really just need to find the antiderivative of x, which means I go up a power and divide by that new power. And then I have to subtract 5 times the antiderivative of 1 over x. That's a very specific antiderivative. It's the natural log of x. Just remember, put some absolute value bars there because we're not really 100% sure where x lives. Now that we're done anti-differentiating, we put a plus c. Because that general antiderivative, when I look at this indefinite integral, I should pick up any function that I can differentiate to get this function, and any function here, whether that c is positive, negative, or 0, regardless, I do get this back. Now I would clean it up just so I would have maybe like 1/10 x squared, or you might write x squared over 10, hey, same thing, minus 5 natural log of x, and then plus c. So you might clean up those fractions in the beginning. That's perfectly fine. So just a couple more examples, not to let this drone on for too long, and it's actually not a very long section. But I wanted to throw this in there. Evaluate from 0 to pi over 3 sine of 2x over sine of x with respect to x. All right, so find the definite integral of 0 to pi over 3. Aha, that is not an indefinite integral. This goes back to definite integrals, which means I need to go use that fundamental theorem of calculus and plug in the upper bound and then subtract, plug in the lower bound once I get the general antiderivative. Now, be careful. Oh boy, I tell you what, and this one's just for fun. I really, really, really hope no one is doing this at this point. X, X, and then giving me something like this. You hate to see it, but I can't even tell you. I can't even tell you that I have seen this before at the calculus level. People doing things like this. This is ridiculous, right? So don't take liberties with simplifying things. Respect all of your trig, respect all of your algebra, respect all that pre-calc. It all has to be there. We know what sine of 2x is. We know that sine of 2x is 2 sine of x cosine of x. We know that. I'm going to look right in the camera and say, we know that, right? And everyone's going to nod their head. That's just an old identity from trig, right? So right now, try to think of a function such that when you differentiated it, you got exactly this ratio. You can't do it. And I dare you to go back and look at all the homework you did, look at all the study guide problems, look at all the exam problems, and then go back and look at your textbook and do every problem from chapter 1, 2, 3, and 4. I guarantee you never differentiated a function out of those hundreds and hundreds and, well, thousands of problems. You never differentiated a function and got exactly this out of it, right? Unless you did literally every problem under the sun for the last 10 years of your life, you probably never came across a function that gave you this as a derivative, so you probably don't automatically know the antiderivative of this, which means you need to rely on some other identities or tools in your toolbox, maybe some algebra, maybe some trig in this case, and write this out. And oh my goodness, look how good this is. Proper cancellation. I am multiplying by an entire sine of x, and then I am dividing by an entire sine of x. No matter what x is, those values will always cancel each other out. So that nice little identity cleans up my definite integral. Again, I'm stressing this is a definite integral, but now it's just 2 cosine x, which is the same thing as 2 times the definite integral from 0 to pi over 3 of cosine of x dx. Now, since 2 is just a standard multiple of a real number 2, I can pull it out front. So now all I have to do is integrate cosine. Is there a function out there such that when I differentiate it, I get cosine? Yes, there is. So the antiderivative of cosine must be that function, that's sine of x. But I don't need this plus c here because I'm not doing an indefinite integral. I am doing a definite integral. So again, you've got to be able to switch back and forth and say that this function now needs to be evaluated from 0 to pi over 3. Right? Again, definite integral, not an indefinite integral. So now that you know how to handle both, they're going to start throwing some definite, some indefinite at you back and forth. You need to be able to, jump back and forth between the two and identify them. So you don't just want to write 2 sine x plus c and circle that, because then you haven't done the integral. This is a definite integral, so I'm going to go in with 2 sine of upper limit gets plugged in first, pi over 3, minus 2 sine of lower limit gets plugged in, that's 0. So there's that second fundamental, or the fundamental theorem of calculus, but the second part plugged in. I found the general antiderivative. I evaluate the upper limit plugged in, and I subtract with the lower limit plugged in. Well, the nice thing about sine of 0 is it's 0. So this is 0 times negative 2. That's not going to contribute anything. I'm just subtracting 0. Don't need it. 2 times sine of pi over 3. Again, if you go look on your unit circle, sine of pi over 3 is root 3 over 2. Cancel, cancel. That's just root 3. Maybe I'll do that in red. I've had a lot of students say, why does that say 8? It's not an 8, it's a 2, and I canceled it out. So there's 2, and I cancel. So a definite integral, you should be getting just a nice final answer that's a nice real number. If you have an indefinite integral, then you should be left with a function plus c, right? Because there's no numbers to plug in, so you're not going to get numbers out of it. But when you see a definite integral like this, you're plugging in numbers, you're evaluating those numbers and getting an output of numbers, so your final answer should just be a number. So again, be careful jumping back and forth between indefinite integrals versus definite integrals. In fact, when you deal with definite integrals, you can see there's a bit more work to do after you integrate. You really got to start plugging in a bunch of numbers and finding a bunch of values, and that's a lot of arithmetic. And if you try to go to your calculator, you'll get some nasty decimals and you won't get exact answers. Whereas indefinite integrals, there are no upper and lower limits to plug in. If you can integrate that thing, and walk away from it, you're done, right? As long as you got a plus c, you're done. So indefinite integrals are a great way to practice integration and not have to worry so much about the arithmetic that comes afterwards. But you do obviously have to practice definite integrals as well, so that you're good with that arithmetic. Okay. Again, not too much more. Here I want to say 2 parts to this. First, let's go ahead and evaluate the definite integral from 0 to 2 pi sine of x dx. That'll be part A. And then for part B, we want to find the area enclosed by the curve y equals sine of x and the x-axis from x equals 0 to x equal 2 pi. There should be something that really sticks out in part B, and that thing that sticks out is this word area. When we talk about a definite integral or an indefinite integral, there is no mention of area. No one considers area. Why would you even bring up area? All we're doing is taking this mathematical concept and finding a value. But when you read a word problem that has the word area in it, you need to specifically hone in on how much space is there. And that's the only time you worry about area is when they say the word area. So for part A, all we have to do is look at the integral from 0 to 2 pi sine of x dx. Is there a function out there whose derivative is sine of x? Yes, there is, and that is negative cosine x. Don't forget the negative, because if you differentiate cosine of x, you get negative sine, and that's not negative sine. But if I differentiate negative cosine, I would get positive sine. So I want to be sure that I'm getting the correct and proper antiderivative before I start plugging in my bounds. So I'm going to have to go from 0 to 2 pi. Now I can take this, plug in my upper bound, again being very careful about the fact that there's a negative here, minus, again being very careful that there's a negative in the function, but I'm also subtracting, so that's minus a negative cosine of 0. Upper bounds in, I subtract lower bounds in. Well, funny thing about this is cosine of 2 pi, I'm just doing a whole trip around, so when I look at negative cosine of 2 pi. That's the same thing as cosine of 0, but with a negative in front. So that is 1 with a negative in front. Minus minus means I'm adding cosine of 0, which means I'm adding 1, which means my result is 0. So what we call this is evaluating the definite integral. This is the value of the definite integral. Nowhere in part A in the question, nowhere in part A in the solution is there mention of the word area. Now, funny thing is, for part B, they want us to find the area enclosed by this curve y equals sine of x and the x-axis from 0 to 2 pi. They want us to find, let's do this. We'll do pi over 2 pi. Let's extend that. 3 pi over 2, 2 pi. And this will be 1, and this will be negative 1. I'm going to graph this sine function, y equals sine of x. So I'm going to graph it. It starts at 0. It comes up, hits pi over 2. It's 0 again at pi. It's negative 1 at 3 pi over 2. Goes back to 0 at 2 pi. We get this really nice sine curve. And they want us to know, and again, the scale is not exactly perfect, but they want us to know how much area is enclosed by this blue curve, the x-axis, starting from x equals 0, and going all the way to x equals 2 pi. How much area do I see here? It is definitely not 0, right? There is definitely area there. What's happening is, as you're integrating from 0 out to pi, you're getting a positive value, positive value, positive value for the integral. Then as you go from pi to 2 pi, you're picking up negative values, negative values, negative values for the integral. But as far as area is concerned, a positive value for the integral and a negative value for the integral, since there's the same amount of space there, they're canceling out for the integral, for the value of the integral. But as far as area is concerned, this has to be positive area. This has to be positive area. See the discrepancy? Maybe I'll make it a little clearer here. This is going to be negative based on the integral. This is going to be positive based on the integral. Since they have the same quote-unquote area, positive, negative, they cancel each other out. So when you're looking at the value of an integral, you're picking up positive stuff and then you're picking up negative stuff. It's constantly going to adjust for that. That's what integration does. But when you see the word area, this has to be positive. Area, this has to be positive. So what I have to do is take this and evaluate it from 0 to pi, and then evaluate it from pi to 2 pi, but take the opposite sign. Or, since I know these have the same shape, this one curves up, this one curves down, they have the same area, technically, but one's positive, one's below the curve, so it's giving me the negative. I could find 0 to pi and then just double it to get the other piece. So here's one way of doing it. I'm not going to do it both ways. One way of doing it is go from 0 to pi and then double it, because you'll get a positive number, and then you'll double that positive number to pick up the missing stuff here. The other way to do it is to integrate from 0 to pi, right? Break it up. Sine of x with respect to x. And then rather than adding this negative amount, pi to 2 pi, rather than adding a negative, I'm going to subtract the negative to make it positive from pi to 2 pi, sine of x. This is contributing positive stuff, so I want positive for area. This is contributing negative stuff. I don't want negative stuff for area, so I negate the negative stuff to get positive stuff for area. So again, but just by them simply throwing this 4-letter word at you, you now have to completely adjust your integration. because there is not zero area here. So if I run the risk of just jumping on it and going from 0 to 2 pi and say there's no area, obviously I can look at this and say, you're wrong, right? There's definitely area there. There is definitely something that you have to cover. So now I integrate sine of x from 0 to pi. That's negative cosine of x from 0 to pi. Then I want to subtract the integral of sine of x, which is negative cosine of x, and evaluate that from pi to 2 pi. So I have to split it up. These are different bounds, right? So I have to do this one separately. This will give me negative cosine of pi minus negative cosine of 0 minus, and I do have to take all of this and subtract all of this. So this is subtraction. This is negative cosine of 2 pi minus negative cosine of pi. Again, respecting those upper limits minus those lower limits. So when I look at this, cosine of pi, so over here is negative 1, so that's negative negative 1. That is actually positive 1. Minus minus means I'm adding. Cosine of 0 is 1. Minus cosine of 2 pi all the way around is 1, but that's a negative, so that's a negative 1. Minus minus is a plus. Cosine of pi is negative 1, so I'm adding negative 1, aka negative 1 plus a negative 1, that's a negative 2 that I'm subtracting. Here's a 2. 2 minus negative 2 is 2 plus 2, which is 4. So when you talk about the word area, oh boy, you better be careful that you're not negating stuff by going and doing it all in one swoop. You really need to graph the function and look at it so that you know what area you're picking up, so that you know that you're not negating things. Right? If I just swept from 0 to pi, then there'd be no reason for me to have to adjust anything. If I just swept from pi to 2 pi, I would get a negative number, and that would not be nice. But if I go from 0 to 2 pi, I get some positive, some negative, then I need to do some adjusting. I need to be able to adjust a little bit so that I pick up nothing but positive area. So the negative stuff has to be negated, or take the absolute value of. That's another way of doing it as well. Okay, let me go to the book and see if I can maybe pick up one more example, and then I guess we can wrap it up there. That should be good. Here we go. This one, let me erase that. You could call this a quote-unquote word problem if you want, but it's pretty cheap as far as a word problem goes. But at least it gives us an application other than area. This will give us more of an application to something, I would say physics, I guess. So we looked at the position function, the velocity function, which is the derivative of the position function, and the acceleration function, which is the derivative of the velocity function. Now we know how to go backwards because we have anti-differentiation. We could start with acceleration and work back to velocity, or we could start with velocity and work back to position. So that'll be a nice little application. I'm going to steal, this will be actually number 60 out of the textbook here, but I'll write it down for us. It says the velocity function in meters per second is given for a particle moving along the line, and they want us to find A, the displacement, which is position, displacement meaning position, where is it? And B, the distance traveled. By the particle. During the given, well, let's see if I can squeeze it in, interval, perfect. So they want us to find the displacement and the distance traveled by the particle during that given interval. So let's take a look at the velocity that they give us, which is t squared minus 2t minus 3. And they want us to look at this over the interval of t equals 2 to t equals 4. So again, t is time, our time is in seconds. So let's take this velocity. Since we want our displacement, we're going to need our position function. So we're going to integrate the velocity function with respect to t, which means we're going to be integrating t squared minus 2t minus 3 dt, which is just a nice polynomial. So this will give us 1/3 t cubed minus t squared minus 3t plus c. So this will give us our position function, which again we usually denote s of t, just like that. So now we want to figure out what that displacement is. Total displacement, we'll look at the integral from, here is where t starts and where t stops. We'll see what that displacement gives us by going from 2 to 4 of t squared minus 2t minus 3, which is our velocity, which spits out our position, 1/3 t cubed minus t squared minus 3t. But I no longer need the plus c for my position function. I want to find total displacement. So I simply integrate the velocity to get the displacement, and I evaluate that position function from start to finish. So now I'm going to plug in 4. I'm going to get 1/3 times 4 cubed minus 4 squared minus 3 times 4. There's my upper bound plugged in. Minus, now make sure you're subtracting all of this, 1/3 2 cubed minus 2 squared minus 3 times 2. Make sure you're subtracting all that lower bound plugged in, not just the first term. So let's start figuring out what we get. This is going to be 4 cubed over 3, which is 64/3, minus, this will be 16. But if I multiply 16 by 3, I'll get 48/3. I'm just going to go ahead and get a common denominator. We're going to need it anyway. Minus 12, which is 36/3. So I'll get a number for there, minus. Over here we'll have 8/3 minus 4, but I'm going to have to multiply to get 12/3, common denominator, minus 6, which will be minus 18/3. So again, lots of stuff. You know what? Rather than make a silly mistake at this point, since I see my calculator, I'm going to grab my calculator. There's no reason not to. Just be careful about these negative signs. So everything's being divided by 3. So we want 64 minus 48 minus 36 minus 8 minus minus is plus 12 minus minus is plus 18, which will be 2/3. All right, so everything in the numerator is going to be positive 64, negative 48, negative 36, negative 8, negative, negative, positive 12, negative, negative, positive 18. Oh boy, we'll actually just end up with 2/3 in the end. So since we're talking about displacement, we're just talking meters. Right? We've integrated the velocity to get position, so now we just have our meters left over. So the next thing it wants to know is the total distance traveled. Well, you know, this thing could have traveled forward and then backwards. Right? That's sort of the issue that they're making sure we don't ignore here. So we've got 2/3, that's part A, for the total displacement. I should never, well, it's right there. I'm going to say I shouldn't have erased that. We should have kept that t squared minus 2t minus 3. Should have kept that. 2 to 4. So we know part A is 2/3 meters for our displacement. But how far did the particle move? It might not necessarily be the same. Let's take a look at this. T minus 3 times t plus 1 is how that velocity function factors, which means it has a 0 at -1 and a 0 at +3, and it is a quadratic. So by going through and integrating this, it's a quadratic with a positive leading coefficient. By integrating this from +2 to +4, which are our lower limits and upper limits, here's our lower limit of integration. Here's our upper limit of integration. Notice when we go through with all of that, some of this displacement from 2 to 3 was negative, and some of this was positive. We integrated this function across from 2 to 4. We got some negative values and we got some positive values. And the value that we finally got in the end was a positive 2/3. So this had a little bit more room, more positive stuff. This was more, or actually I should say this was less negative stuff. Okay, I didn't draw it perfectly to scale. This should be smaller than the positive stuff. But you can see what happens. Some stuff is canceling each other out. So when it comes to seeing how far that particle moved during that interval, we're going to have to take that into effect. We're going to have to make this negative area positive. And we're going to have to take this positive and just leave it as is. So instead what we want is, for part B, we want to integrate our velocity function from 2 to 3, which is t squared minus 2t minus 3 dt. And we don't want the positive version because the positive version's actually, or sorry, the way I said that's kind of confusing. We don't want that version because it's negative. We want the positive version, right? So that we can get positive stuff and positive stuff to see the total amount that this moved. So I'm going to negate that integral. The other way of doing this is if you remember properties of integrals, you can flip the lower and upper bounds and you automatically get the opposite sign. But I'm just going to put the negative there. Now when we integrate from 3 to 4, it's positive stuff, and we want positive stuff because we want to know how far it traveled. Whether it traveled some ways backwards and then some ways forwards, doesn't really matter. We want to know the total distance traveled. And if it goes forwards the same amount it goes backwards, it might negate itself and give us 0. We don't want 0. If it goes forwards, we count that as positive distance. If it goes backwards, we count that as positive distance. So we have to work it by splitting it up down the middle to get our, basically this relates to like, the total positive area. So let's just take our time with this. 1/3 t cubed minus t squared minus 3t. We're going to evaluate that from 2 to 3, plus, we'll do the next one, and we will do, just trying to draw an arrow there, so plus we will do 1/3 t cubed minus t squared minus 3t, but that one goes from 3 to 4. So because, and I did see, I almost didn't put the negative there, because otherwise this would give us a negative quantity, but now it's going to give us a negative quantity that we're going to negate, and we'll get the positive version. So there's a negative out front. We'll plug in the upper bound of 3, 1/3 3 cubed minus 3 squared minus 3 times 3. There's my upper bound. Maybe we'll bring some color in here. There's my upper bound. Minus, now here's my lower bound plugged in, 1/3 2 cubed minus 2 squared minus 3 times 2. Now I have to take that and negate it all, which is why I have this negative out front of those brackets. Now I have to add on my upper bound of 4 plugged in, 1/3 4 cubed minus 4 squared minus 3 times 4. There is my upper bound of 4 plugged in. Now I have to subtract my lower bound plugged in, which is going to be 1/3 3 cubed minus 3 squared minus 3t. Boy, that's hard to fit in. Again, I don't have the same whiteboards as SCF has. I got to use my own personal whiteboard. One of these days I'll get a 10-foot whiteboard. So this whole painstaking process would be something that would be, very, very tedious. I mean, not too terrible to compute, but pretty tedious, right? So what I'm going to do is, and for the sake of time, just kind of simplify this a little bit and then plug it in the calculator to make sure I get the right answer. This is 27/3, which is 9, minus 9 is 3 squared. So these are even canceling out. Minus 9 here. Now make sure you're keeping that negative out front. There's also another negative. This is 8/3 minus 4 minus 6. So I've done the first part plus. Now I'm going to have 4 cubed is 64 over 3 minus 16 minus 12. There's my upper bound. Minus 3 cubed over 1/3. That's 27/3. That's me subtracting the whole quantity 9 minus 9. Again, those cancel. Minus 3. Oh, I put a t there. Sorry, I meant to put a 3 there. Minus 9. There we go. There's the lower plugged in. Now again, just because of space and in the sake of not messing this up at the very last second, let's see what we've got here. Negative 9, and then I'm going to subtract 8/3. Then I'm going to subtract 10, because that's what minus 4 minus 6 is. And I'll close off those parentheses. And then I'm going to add this quantity here is going to be 64/3 minus 28, because that's what negative 16 and negative 12 is. And then I'm going to subtract negative 9, which means I'm going to add 9 to that. And we actually get pretty lucky here because, oh, I know what I forgot. I was like, wait, there's no way we're getting the same answer. Remember, we need to negate this first part. So all this stuff needs to be negated, which I'm just going to go back and negate that real quick. So I'm going to have make sure I can do that without messing anything up. So that should be 7/3 in the end. And this was our displacement. Or sorry, not our displacement, the total distance traveled. Because again, by looking at that velocity function, it was decelerating and it was then accelerating, or sorry, it was slowing down its rate of change and increasing its rate of change. That velocity function was negative over some time and positive over some time. So it was moving backwards and then it was moving forwards. And we want to not cancel those out by having them overlap. When it moved backwards, we wanted to count that as forward movement, just in the other direction. And then it moved forward from 3 to 4. We wanted to count that as well as forward direction. So the total distance it traveled, right? If I start here and travel a foot and then back a foot, I didn't travel 0 feet. I traveled 2 feet. And that's what this process does, is it splits it up so that it counts me moving down a foot as moving a foot and then moving up a foot as moving a foot. I said down and up, it's kind of crisscross there, whatever. So again, just something other than area that we can talk about. So we can interpret it as more like forward and backward movement. But you can see the integration. It's, definite integrals here that we have to solve, which is slightly different than indefinite integrals. I know it's in this section, but again, brings it all into the big picture. Indefinite integrals, make sure you're getting your plus C. Definite integrals, make sure you're plugging in those upper and lower bounds and computing them accordingly. You should not have a plus C when you're done with a definite integral, but you have to have a plus C when you have an indefinite integral. Let's see where that time is at. That is, 1 hour and 20 minutes, should be right on the money. So last section will be 5.5, where we'll do a bunch more indefinite integration, maybe some definite integration as well. Yeah, I'll say yes, some definite integration as well. That'll be the last section, and that'll give us the most powerful technique for finding antiderivatives or doing integration, as they say. So 5.5 will be pretty important. So stay tuned for that. And then that'll be the last section. And then we'll be ready for exam 4. And then I'll make a video for the final exam explaining, more specifically what I'm going to be putting on the final exam, how many questions and how long and stuff like that. I'll mention that again in 5.5, that I'll make another video for the final exam specifically, because I think it deserves its own little refresher as well. So thank you very much, and I'll see you in the next section.